I will begin this tutorial with two quick animations, just to show you what it is that I will be setting up later on. Here you can see the velocity profiles develop as the piston pushes the air, forcing open the reed valve, and the valve closing as the piston slows to a stop. Notice that the velocity is 0 in this area above the valve. This region is defined as porous media, and you can think of it as a gasket that is stopping the flow. This second animation shows the moving and deforming mesh that helped Fluent calculate the velocity profiles in the previous animation. This tutorial will give you the basic information you need to be able to properly set up a dynamic mesh problem. As such, I will gloss over some of the other settings and focus on what you need to know to get your problem defined correctly the first time. I have already loaded a case file into Fluent and specified a few settings including the transient solver, energy and turbulence models, and air as a compressible fluid using the ideal gas law. I have also already defined the region above the valve as porous media using a UDF. I have split the domain into several different cell zones. This first area, filled with hexahedral cells, is where I will use the layering technique. This region containing the valve is divided into 3 zones: the prism layers around the valve, the triangular mesh zone, and the prism layers on the stationary walls. This final area is the stationary mesh outlet. I will go into greater detail about these zones while I am defining the dynamic mesh. The next part of this setup is the boundary conditions. The only setting to note is that the exit here, it is set as a pressure outlet, with 0 relative pressure and reasonable backflow turbulent quantities. Now, to define the dynamic mesh for this case, I need to enable dynamic mesh. I know that I will be using layering for this zone, and smoothing and remeshing in this zone, so I will activate all 3 of these options. I also know that I want this valve to open due to the forces acting on it, so to be able to do this I need to activate the 6 degrees of freedom or a 6-DOF solver. I will start by defining this piston's motion by creating a dynamic mesh zone, and this boundary is called inlet. The piston will be moved by rigid body motion, and it will not be moved using the 6-DOF solver. Instead, I will use a profile to describe the motion of the piston. This profile specifies when the piston will begin to accelerate and when it will slow to a stop. Now that it is loaded, I can set the motion to this profile. Before I can create this zone, I need to go into meshing options to specify a cell height. The cell height is the height of the cell that is normal to the direction of motion, and it is used in the layering technique. This cell height of 0.01 meters is the width of the cell wall, here. It is important to have the same height on each cell row throughout the domain. This zone is called fluid layering, and the mesh will be deforming. I want to ensure that only the layering technique is used here, so I've disabled smoothing and remeshing. Next, I can go on to define the motion for the valve. It will be moved by rigid body motion, and in this case I will be using the 6-DOF solver. And now I need to point to a UDF that describes the 6-DOF settings. Now I can give you a quick look at the text file for this UDF. This specifies the mass of the valve. This is its moment of inertia. These specify which degree of freedom is free to move. As you can see, it is only free to rotate about z. X, y, and z translation is fixed, as is the rotation for x and y. I also have a simple sine function to define the gravitational force on the valve. Now that I have loaded this UDF, I can select it. The final thing that I need to do is to remove the cell height, as it has no meaning here, and create. I also want the prism cells around the valve to move with the valve. This is the prism layer around the valve. It will be moved as a rigid body, and its motion will be calculated by the 6-DOF solver. But I do not want the forces and moments of this zone to be taken into consideration, so I have enabled passive zone. The next zone that I want to specify is fluid remeshing, and as I display this zone you can see that it is filled with triangles that will be deforming. For mesh options I want to use smoothing and remeshing. By clicking zone scale info I can see what properties the mesh already has to populate the minimum length scale, maximum length scale, and maximum skewness that will be used to determine when to remesh this zone. Now I can close the zone scale info dialog box and create this zone. The final zone that I need to specify is fluid stationary prisms. This zone just needs to remain stationary while the mesh around it is moving and deforming. This concludes the local setup for the 6 different dynamic mesh zones. I encourage you to watch the follow-up video to this one, which covers other good practices for when you are defining a dynamic mesh problem. It will pick up where I left off in this video.